Okay, let's start. Today we'll be studying discrete random variables. Here is the outline of the lesson. First, we'll introduce random variables and then probability mass function and some discrete random variable types. And then we'll look at CDF, how to construct CDF, followed by average and expected value. Next, we'll look at random variable derived from another one, and finally expected value of derived random variables, variance and standard deviation. Okay, a random variable consists of an experiment so we have an experiment, and we have a probability measure regarding with this experiment. So we got a sample space, and then we define a function, okay, that assigns a real number to each outcome of this sample space. So this is illustrated in here. We got the sample space, we have outcomes in here, and we make up some events in here, either individual outcome as an event or a group of outcomes as an event. And we define a random variable whose values might change from -infinity to +infinity. And then we assign a probability to the numbers of these, the values of random variable. Here's an example. You see here, we got six IC, so 6 IC, and we test these ICs, whether they are accepted or rejected. So we take one IC and ask, test it, rejected or accepted. Take the next one, rejected or accepted. In each observation here is a sequence of 6 letters then. Let's say rejected, 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 goes to accepted, 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 accepted. Okay, so any outcome of the experiment will be combination of these letters. The sample space then consists of 64 outcomes, and we can define a random variable for this experiment. Let's say n is a random variable, which is the number of accepted ICs. Okay, so for this outcome, since we got 6 ICs, then there may be no accepted IC, then n is going to be 0. When there is one accepted IC, then n is going to be 1. So on, and then finally, if all 6 ICs are accepted, n is going to be 6. So the sample space of this random variable is going to be, the values of this random variable, range of random variable will be 0 to 6. Okay? Now, we can then assign probability of this and then continue other examples. PMF is one of the important functions that we'll be using in probability theory. Simply, we use a capital X to denote the probability mass function, with X subscript, capital X, which refers to the random variable, and X is the argument, so the values of random variable. Okay, And it's equal to probability that the random variable is equal to the specific value of that random variable. Okay, for example, in previous example, we can write Pn, so n here is the random variable, n is probability that n, the number of accepted ICs, is equal to 1, for example. Or P n equal n. Here, n could take the values 0 to 1 and 6. Okay, so here we see some of the properties of probability mass function. That is a positive number, positive function. It starts from 0. The minimum value is 0 and goes to 1. So it's a number between 0 to 1. It's a function whose values will be between 0 to 1. And some of the PMF should give you 1. And for any event B, which is subset of Sx, for any x random variable, then probability of B will be the PMF function, sum of the probability values at every x value within this B. Let's see this example. We have a basketball player here, Wilt Chamberlain. I don't know this player, but it seems that it might be very famous basketball player in NBA probably. And he shot 2 free throws. Each shot was equally likely either to be good or bad. So let's say the first shot, good or bad. And since there are 2 shots, the next will be good or bad. So if the first one is bad, the next one will be good or bad. Okay, so this is a simple tree diagram showing this experiment. Each shot that was good was worth 1. So if it is good, then we got 1 point here. If it is good, there is 1 point here. And if it is bad, we got 0. Bad, 0. Good, 1. Bad, 0. What is the PMF of X? The number of points that he scored. Okay, let's see the values here. This is equal to likely, then this is going to be 1 over 2, 1 over 2, so 1 over 2, 1 over 2. Let's look at the points that he scored. If this good, then that's going to be 1. If this, 2, I'm sorry. So 1 plus 1, 2 points. And first good, bad, 1, 0, so 1. Bad, good, 1. And bad, 0. So the range of X, then could be 0, 1, and 2. So the total number of scores that he may get with this free shots, it might be 0, where there is no good, all are bad. It might be 1, so one of the shots will be good. It might be 2, where 2 shots are good. So from this, then we can make a table like that instead of a tree diagram, where we got the outcomes. You see here the outcome here is good, 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 bad, bad, good, and bad, bad. Okay, so there are 4 outcomes, and each of them has different probability. All of them have equal probability. But if I look at the score here, then we see that you might get 1 twice, and 2, 1, and then 0, 1. So the probabilities will be different for X, right? Since there are here 4, then we can write the probability of X, so the score is 0, will be, since there is just one outcome, so 1 over simply 4. 1 over 4. I'm sorry. Probability of X equal to, so 2 points, is again 1 over 4. Why? Because we got just 2 points. But we have 2 1 points. So probability of X equal 1 will be 2 times 1 over 4. So 1 over 2. You see, sum of this should be 1. Okay? 1 over 4 plus 1 over 4 plus 1 over 2 gives you 1. So sum of this PMF should be 1. Then we can plot a PMF function here then. Okay, if we want. Here is X. Here is Px of X. We got the values here 0, 1, and 2. So before 0, here, it's 0. When it is 0, probability increases 1 over 4. So here is 1 over 4, goes to 1. And then when it is 1, then that's going to be 1 over 4 plus 1 over 2, which is 3 over 4. I'm sorry. 3 over 4. So this increases to 3 over 4. So this is 1 over 4. This is 3 over 4. And then finally, when it is 2, then it becomes, I'm sorry. Okay, sorry. This is CDF. I'm sorry. I'm sorry. We just make CDF. Okay, let us indicate that. That's CDF. So it is sometimes called fx of x. For PMF, that's quite easy. I'm confused with that. Okay, so here, again, let us draw it. X, 0, 1, 2. So fx of x. Okay. Or sometimes we use capital X of x. I'm sorry, this is not correct. Let me erase it. Okay, this is, so this is fx of x, the CDF, okay? Or sometimes we use fx of x. So here is our px of x. We have already determined this. So for 0, it's 1 over 4. So this is 1 over 4. For 1, I don't know what is happening, but it's switched between the slides. So for 1, it is 1 over 2. And for 2, again, 1 over 4. Okay, so here is how we plot PMF. And here is how we plot CDF. You have already studied CDF from the lecture, no? So this is somehow here we derived CDF earlier. Okay. So here we go. You see, for 0 is 1 over 4, 1 over 2, and 1 over 4. Any question?
No
Next.
question, teacher.
Okay, thank you. Families of discrete random variables. Here we have some experiments. As you can see here, we define some random variables here, x. Every time we got 2 outcomes, you see, head or tail here, which is typical coin flipping. And the other one is a random. We choose a random student and look at the phone number and then the last digit of the phone number. It might be either even or odd. And probability result will be 0 and 1. Okay. Next, we have we look at the bits transmitted by a modem when downloading a file from the internet, and X is either binary 0 or 1. So the result is 0, 1. So in such two outcomes, we assign a probability to one of these outcomes, and if they are equally likely, then we simply write probability of H is probability of T equal 1 over 2, typically. This is also the same. Now, then we define Bernoulli random variable. Bernoulli random variable has this PMF, you see. So when the random variable takes the value of 0, then the probability is 1 over P. When it is 1, probability is P. So sum of this should be unity, of course. Otherwise, that is 0. So we can plot it simply. Here is 0, here is 1. So the probability is P. Let's say this is P, then this is going to be 1 minus P. If P is 1 over 2, then these are equally likely outcomes, okay? Usually this P is in between 0 to 1. It's not 1, it's not 0, it's something between them. If they are equally likely, we take its half. Geometric random variable, this random variable has this form. So the idea is the same. We got the probability value, P, and we got the values of X here, which starts from 1 and goes to the number of X, whatever it is. And in example 3.9, as you can see, we got an example. We got an experiment where we can use this geometric random variable. We got the IC testing again. This is a very classical, example that we have been using in this course. We test whether they are accepted or rejected. And here, the rejected probability is given. So probability of rejected is a P, then this is going to be 1 minus P. Okay. Now, what is the PMF of Y? If Y is the number of tests up to the first reject. Okay. So we can again draw a tree diagram. Let's say I take the first chip and look at whether it is accepted or not. If it is accepted, then we got a probability of 1 minus P. We got accepted, and we got rejected. Then Y here will be 1. So the number of rejected, right? R. Next, if I got as accepted, then I try another one, another test. Again, I may get rejected or accepted. Then Y is going to be 2. Okay, so the first one and the second one. So Y is going to be 2. Next, accepted, rejected. Y is going to be 3. So it goes like this. Okay, so what I am looking for here, simply I just want to get, okay, the rejected, okay, the first rejected. First rejected might occur in the first test, or in the second test, or the third test, or the first test. So we have to determine each of these probabilities. For Y, for example, for Y is 1, then probability of Y equals 1 is going to be, since this is P, Okay? For y equal to the probability of y equals 2 is going to be 1 minus p times p. So 1 minus p times p. Okay? Next, y equals 3. So probability that y equals 3, which is 1 minus p times, here again, 1 minus p. Okay? Times p. So it goes like this. Then I can write probability of y equals y. So any number of y, it's going to be p times 1 minus p to the power of y minus 1. Okay? For example, here, you see this is 3. Then here we got 1 minus p to the power 2, which is y minus 1. Y is here 3. Okay. So this experiment and this random variable is geometric random variable. We got one more example here. For PMF, you see we plot py of y. You can use MATLAB or by calculation, you can draw PMF. Binomial random variable. This is another common random variable that we see. Here, for any x, if it is a binomial random variable with NP, these are the parameters, okay, N and P, the PMF is given by this expression, Py of x is Nx. So choose x over n, right, out of n. And this is very similar to geometric random variable, right? And the first Bernoulli random variable. Here, we have again IC circuit test. In a sequence of n independent tests, so we got n tests, and each circuit is rejected with probability p again. So we again get an IC, test it. If it is rejected or accepted, probability of rejection is p. So probability of accepted chip is 1 minus p. Let us write it again. 1 minus p. Okay. Now let k equal the number of rejects in n tests. So we got k rejects out of n tests. So this is simply binomial random variable. Okay. So pk, k is a binomial random variable. So if we got such experiments, similar models, then we can use binomial random variable. Here, choose k of n here. So p is the probability of rejected IC, and n and k are given. For any number of tests, we can find the probability of k rejects by using binomial random variable. And here we see the PMF graph here. To draw this graph, we have to put into all values in here, k and n, and determine the specific values of PMF at that value. Okay, CDF. Remember PDF. Again, Px of x was probability that x, the random variable, is equal to the specific outcome of that random variable x. Now in CDF, cumulative distribution function, which is denoted by capital F. So f x of f. Here, probability, we look at probability of x, the random variable, less than or equal to x. Not equal to x, but less than or equal to x. Okay? So here is the properties of CDF for any random, discrete random variable x, whose outcomes might be x1, x2, and so on. If x1 is less than or equal to x2, so this is ordered outcomes, then we can use this for properties. The first one, the CDF of minus infinity is 0, and CDF of plus infinity is 1. So CDF is a function between 0 to 1. Okay? It starts from 0 and increases to 1. For any x prime of x prime, which is greater than x, the CDF at that x prime is greater than the CDF of x. Okay? And one of the most important theorem that we'll be using is the values of CDF. If we are given any B and A, where B is greater than A, then fxB minus fxa can be written in terms of probability of value of x is in between A to B. So if we look at the probability of a random variable in between two numbers, two values, we can use the CDF at those values. Here's an example. We have already remembered this picture. Let's go back to that slide. We have, I made a mistake here, as you might remember, and plot this function. You remember? Okay. So we have already solved this example. This is how we switch from PMF to CDF, okay? We simply look at the range of CDF when x is less than 0, or x equals 0 is given here. It's an increasing function. As you can see, we have 0 until 0, and then it increases 1 over 4. So this is 1 over 4. And then goes to 1. So when it is 1, it's 1 over 2. So this is 1 over 2. You see 1 over 2 plus 1 over 4, which is 3 over 4. So it increases 3 over 4, you see here. Okay, goes to until 2. When it is 2, we add 3 over 2 plus 1 over 4, which is 4 over 4, which is 1. So 1. So we simply add the values of PMF and accumulate it. So that's an increasing, monotonically increasing function, as you see typically. So CDF always start from 0 and always end up with 1. Okay? This is 1. Be careful. We have one more example. You can plot this. Average and expected value. Average is a number that describes a set of experimental observations, and along with this average, we have mode, median value, and expected value, which is actually mean value. Okay, so these are different terms. We can show that in this example, better to understand how we determine mean value, median value, and the mode. Here we got the quiz result. And I got 10 students, and the grades are here out of the scale 0 to 10. So I can put them in order. Let's say 1, 5 here, so 5, another 5, and another 5. Okay. And I got 4, I'm sorry, here first. And next I got 7. How many 7? I got 1 here, another here. So 7, 7. And then 8, 2 8s. Okay. And then 1 9. And then 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 students. So I ordered them from the minimum to the maximum. Now we got some of this first. We have to add them up. So we add them up and then get the total, which is 68. You can easily prove it. Then the mean value from this formula, okay, we can determine the mean value. But here, since the probabilities are equal, then we just add them up and divide by the number of outcomes, 10, which is 6.8. Okay, the average value or the expected value or the mean value is 6.8. How about the median? Median is the number where we got half of the outcomes below this. Okay, half of them is above this number. Here we can easily see that that's 7 because we got 4 numbers before 7 and 4 numbers after 7. So then 7 will be the median value. Okay, next, mode. Here the mode is 5 because 3 students have a grade of 5. So simply we look at the grade where most of the students, the highest number of students received this number. Here it's apparently 5 because 3 students received 5. Okay. Any question? Functions of a random variable. We can define new random variables using a random variable. Let's say x is a random variable. Then I can define another random variable y, which is a function of x. For example, I can write y equals x squared, or y equals, let's say, 3x. So whenever we got a random variable here, then we can have, we may have another random variable derived from this one. Here, how to write PMF of y? PMF of y, simply we determine the values of y by taking the PMF of x over the values where g of x is equal to y. Okay? Here is an example. You can have a look at this example. There is a trick here, by the way, how to formulate this. Please study this, and if you have any question, we can talk about that later. Here is an example. The amplitude volts of a sinusoidal signal is a random variable, whose PMF is given here. So you see the range of voltage is -3, -1, -2, -1, 0, 1, 2, and 3. So the number of values here is 7, as you see. And it is, PMF is given here, so that's uniform. Uniform random variable. It's called uniform random variable. You can have a look at the textbook where you can find uniform random variable. And the probability is 1/7 because we have 7 outcomes here. So the probability of each will be 1/7. Now, we define a new random variable. y. And y is v squared over 2. So then we can determine the values of y with the outcomes of v. Let's say this is v and this is y. V takes on the values minus 2, 3, minus 2, minus 1. I'm sorry. Minus 1, 0, 1, 2, and 3. Now let's determine y, which is v squared over 2. So 3 squared 9, 9 over 2, 4.5. 2 squared 4, 4 divided by 2, 2. 1 squared 1 over 2, 0.5. 0 is 0, 1 is again 0.5, 2 is again 2, and 3 is 4.5. So then is y simply 0, 0.5, 2, and 4.5. Okay? Then I can construct my PMF, right? Okay, I can construct my PMF. How? You see probability of 0.5. Let's count the number here. 1, 2, 3, 4, 5, 6, 7. So probability of, I mean here, the probability should be 1 over 7 for each. But since I have 2.5, then that's going to be 2 over 7. Since I got 1.5, then the probability will be 2 over 7. So simply for PMF, I can write PMF of this random variable. When y equals 0, that is 1 over 7, because there is just 1 0. But I have 2.5s and 2 2s and 2.5s. Okay? So then each will be 2 over 7. When y equals 0.5 or 2 or 4.5, the probability is 2 over 7. Okay? And for all other values, it's 0. So here is how to construct PMF. We can also make a CDF for this, right? Yes, we can. How? You see, simply add this value to here, and then add this one to here, and add this one to here. So we'll get simply an increasing function like this again. Okay, you can try this. Expected value of a derived random variable. As we can see in previous slide, we got y, which is a function of x. If this is given, as in previous example, it was v squared over 2. So we can use the expected value. We can determine the expected value by using this formula. And the expected value of x minus mu x is equal to 0, because this is, you see, this x is equal to mu x. And expected value of ax plus b, a times expected value of x plus b, that's a linear operation. You see in this example, px is given, y is given, so we can construct y from here, and then we can determine expected value of y using this equation. Okay. Variance and standard deviation. Variance of a random variable is given with this formula. We can expand this. So expected value of square of this minus 2 times x mu x and plus mu x squared. Okay, so we can use this here as you can see, expected value of x mu x is going to be mu x, expected value of x, which is mu x times mu x, which is mu x squared. So then this could be written as x squared minus 2 mu x squared plus mu x squared. Okay, then it's going to be x squared minus mu x squared. This is equivalent to this one. Okay, we can also define moments. Moments is simply expectation of x to the power n. So expectation of x to the power n. And we can define central moment, which is the normalized version of this moments by the mean value. And we can also define standard deviation, which is the square root of variance. So here is the list of the variance values for different random variables: Bernoulli, geometric, binomial, Pascal, discrete, uniform, and Poisson random variables. Okay, this is the last slide. Remember the formula here. Okay, where is it? Here we go. I'm sorry. So this equation, identity, sorry. So remember this. Expectation of ax plus b, for example, which is a times expectation of x plus b. So we can use this to derive expected value of y when y is equal to x plus 1. We can also determine its variance by using this formula. Okay, so variance of a x squared b is a squared variance x. Okay, so here we are given a voltage value with this PMF, and now the new voltmeter records the amplitude in millivolts. So if we have a V here, let's say minus 3 goes 3, okay? So what about U? This is volt, this is millivolt. So minus 3 volt is equal to minus 3000 millivolt. So 3 volt will be 3000 volt, sorry, millivolt. So we can write U, then U is equal to 1000 times V. Okay, this is our new random variable. This is the old one. This is the new one, so the derived random variable. And how to determine its expected value? We can easily use the formula, the summation of let's say G U product of V. We can use this formula to find mu V, or we can use this simple expression. So both are given here. For variance, you see it uses simple formula here instead of deriving random variable, sorry, variance from this equation. Okay, this is the last slide. Do you have any question? Any question?
No, teacher. No question.